Take a deep breath. Feel the air fill your lungs. That gas you just pulled in, the oxygen, is the reason you're alive. It powers every cell in your body. It's so fundamental to our existence that we barely think about it. But the Earth wasn't always like this. For the first half of our planet's history, the air was poison. There was almost no free oxygen to breathe. The world was a completely alien place, ruled by life that would be killed by the very air we depend on. The story of how that changed is the story of a global revolution. It was a planetary transformation so profound it makes everything humans have ever done look like a tiny ripple in a pond. It was a period of pollution, a mass extinction, and a climate catastrophe that froze the entire globe. And it was all caused by a new kind of microscopic life that discovered a new way to eat sunlight. This event has a name. Scientists call it the Great Oxidation Event. It's the moment our world learned to breathe. And in doing so, it nearly wiped out all life on Earth. To understand how big a deal this was, you have to picture the early Earth. So let's go back, say, 3 billion years ago. The planet is already old, over 1.5 billion years old. Life has been around for a while, but it's simple. It's all single-celled microbes. There are no plants, no animals, no fish in the sea. The world they live in is strange. The sky probably isn't blue. It's more likely a hazy orange-pink, thick with methane and carbon dioxide. The sun is weaker than it is today, but this thick blanket of greenhouse gases keeps the planet warm enough for liquid water. And the oceans are not blue either. They are probably a pale, murky green. That's because they are full of dissolved iron. Think of it like a planet-sized solution of iron filings mixed in water. When rocks on the continents eroded, iron washed into the sea and just stayed there, dissolved in the water. It couldn't rust, because there was no free oxygen to rust it. The life that existed in this world was tough. These microbes were anaerobes, which is a fancy word meaning they don't use oxygen. In fact, for them, oxygen is a deadly poison. It's a highly reactive, destructive gas that tears apart the delicate machinery inside their cells. So they lived their lives without it. They got their energy from other sources like chemicals bubbling up from deep sea vents, or by breaking down molecules through fermentation. They were the undisputed kings of this ancient oxygen-free world. They had been for over 1 billion years. They had no reason to think things would ever change, but something new was happening in the shallow, sunlit waters. A new kind of microbe had evolved. We call them cyanobacteria. You might know them by their more common name, blue-green algae, though they aren't technically algae. These little guys had figured out a revolutionary trick. It was a new way to make a living, a new way to get energy. It was called photosynthesis. It's a process we're all familiar with today. Plants do it. Algae do it, and cyanobacteria were the first to figure it out. The recipe was simple. They took in carbon dioxide from the water. They took in water itself, and they used the energy from sunlight to combine them and create sugar. The sugar was their food, the fuel that powered their lives. It was an incredibly effective way to live. Sunlight was everywhere, water was everywhere, carbon dioxide was everywhere. They had an endless buffet. But this new process had a byproduct, a waste product. Every time a cyanobacteria made a molecule of sugar for itself, it released a molecule of something else. That something else was oxygen. For the cyanobacteria, oxygen was just trash. It was something they had to get rid of to keep their internal chemistry working. They pumped it out into the water around them, not knowing, not caring that they were releasing a substance that would one day change the entire planet. For a long, long time, this didn't make much of a difference. The cyanobacteria were just one type of life among many. They started to grow in huge colonies, forming mats in shallow coastal areas. Over time, these mats would trap sediment and build up in layers, creating structures called stromatolites. You can still see ancient fossilized stromatolites in the rock record today, looking like stony cabbages. Wow. They are some of the earliest visible signs of life on Earth. And in a few strange salty lagoons, like in Shark Bay, Australia, you can even see living ones still being formed today. These living fossils are a direct link back to the tiny architects that started it all. As these colonies of cyanobacteria grew and spread over millions of years, they were all doing the same thing. They were all taking in sunlight and water and CO2, and they were all pumping out their waste product oxygen. At first, this oxygen didn't build up in the atmosphere. The world had a built-in defense mechanism. Remember all that dissolved iron in the oceans? As soon as a molecule of oxygen was released by a cyanobacterium, it would immediately bump into a dissolved iron atom. And what happens when iron and oxygen meet in water? They rust. So, For hundreds of millions of years, the oceans of the world began to rust. The oxygen would leave the bacteria, find an iron atom, and bond with it to form iron oxide. This iron oxide, or rust, is not soluble in water. It's a solid. So it would precipitate out of the water and fall to the ocean floor like a slow, steady, reddish-brown snow. This snow of rust would settle on the bottom, forming a layer of iron-rich sediment. This process wasn't constant. It likely happened in cycles. Maybe in the summer, when there was more sunlight, the cyanobacteria would bloom and produce a lot of oxygen, causing a layer of rust to fall. In the winter, they'd be less active, and a layer of silica, rich mud, or clay would settle on top. Over millions and millions of years, this created a distinct pattern in the geological record. Layer upon layer of iron-rich rock alternating with iron-poor rock. Geologists call these banded iron formations, or BIFs. These BIFs are enormous. Some are hundreds of meters thick and stretch for thousands of kilometers. The iron ore that we mine today to make steel for our cars and buildings, much of it comes from these ancient formations. They are the physical evidence of the world's first breath. They are the geological tombstone of a world without oxygen. For as long as these BIFs were being formed, it means there was oxygen being produced, but it was being immediately captured by the iron in the oceans. It was being scrubbed out of the environment before it could escape into the air. This went on for a very, very long time, maybe 300 or 400 million years. The cyanobacteria kept pumping out oxygen. The oceans kept rusting. It was a slow planetary scale chemical reaction, but eventually the supply of dissolved iron in the surface waters started to run low. The oceans had rusted about as much as they could. The great iron sink was getting full. The oxygen also reacted with other things. It reacted with minerals on the land masses, causing the continents to rust. It reacted with gases in the atmosphere, like methane. It was being absorbed by every possible chemical reaction it could find. But the cyanobacteria were relentless. They just kept making more. And then, around 2.4 billion years ago, the planet reached a tipping point. The sinks were full. There was just nowhere else for the oxygen to go. It had saturated the oceans. It had rusted the minerals. Now, for the first time, the free oxygen began to escape the oceans and build up in the atmosphere. This is the moment we call the Great Oxidation Event. It wasn't a sudden explosion. It was a slow accumulation, but from a geological perspective, it was an event. The concentration of oxygen in the atmosphere, which had been less than 1 part in a million, started to climb. It rose to maybe 1% or a few percent of the atmosphere. That doesn't sound like much compared to the 21% we have today, but for the life on Earth at the time, it was an absolute catastrophe. For the anaerobic microbes that had ruled the world for billions of years, this new oxygen-rich atmosphere was hell on Earth. Oxygen, the very thing we need to live, was a corrosive poison to them. It attacked their cells and broke down their biological machinery. They had no defense against it. The result was the first and possibly the most severe mass extinction in the history of our planet. Vast swaths of the life that had dominated the globe were wiped out. It was a holocaust on a microscopic scale. Imagine if the air around you suddenly became a toxic acid. You would have nowhere to run, nowhere to hide. That's what happened to the anaerobes. The world they had known was gone forever, polluted by the waste gas of the upstart cyanobacteria. Life had to make a choice: adapt, retreat, or die. Many died. The world's biodiversity plummeted. Some retreated. They found refuge in places where the oxygen couldn't reach them. They went deep into the mud on the seafloor, into hydrothermal vents bubbling with chemicals, into places that remained oxygen-free. And some of their descendants are still there today. In fact, some of them live inside us, in our own oxygen-poor digestive tracts. They are living relics of a lost world, but the consequences didn't stop with the Great Dying. The entire chemistry of the planet was being rewritten, and this had a dramatic effect on the climate. Before the GOE, the Earth's atmosphere had a lot of methane in it. Methane is a very powerful greenhouse gas, much more potent than carbon dioxide. It was a big part of what was keeping the planet warm, especially since the sun was fainter back then. But what happens when free oxygen and methane meet in the atmosphere? They react. The oxygen breaks the methane down into carbon dioxide and water. Carbon dioxide is still a greenhouse gas, but it's much weaker than methane. So, as oxygen levels rose, methane levels plummeted. The planet's warm, thick blanket was suddenly ripped away. The result was a global deep freeze. With the main greenhouse gas gone, temperatures on Earth crashed. This triggered a period of glaciation so severe that many scientists believe the entire planet froze over, from the poles to the equator. They call this snowball Earth. For millions of years, the globe may have been encased in a thick shell of ice, a white marble hanging in space. The Great Oxidation Event didn't just poison the planet's inhabitants, it also plunged the world into the longest and most severe ice age it has ever known. It was a world altering 1-2 punch of pollution and climate change. It sounds like the end of the story. A world poisoned, then frozen. It could have been, but life is resilient, and in this new, harsh, oxygen rich world, a new possibility emerged. While oxygen was a poison for the old guard, for some organisms, it was an opportunity. A new kind of metabolism evolved: aerobic respiration. This is what we do. It's the process of using oxygen to burn food like sugar to release energy. And it is incredibly powerful. Using oxygen to get energy from a sugar molecule is almost 20 times more efficient than the anaerobic methods that had been used before. With this new high-powered way of living, life could become more complex. All that extra energy could be used to build bigger cells, more complicated structures, and to power more active lifestyles. Oxygen was a poison, yes, but it was also a high-octane fuel. This laid the groundwork for the next great leap in evolution. It allowed for the rise of a new kind of cell, the eukaryotic cell. This is the type of cell that makes up your body and the bodies of every plant, animal, and fungus on Earth. Eukaryotic cells are much larger and more complex than the simple bacterial cells that had come before. They have a nucleus to hold their DNA and a host of other specialized internal compartments. One of those compartments is the mitochondrion. Mitochondria are the power plants of our cells. They are where aerobic respiration happens, where oxygen is used to generate the energy that keeps us going. And the story of how our cells got mitochondria is fascinating. The leading theory is called endosymbiosis. It suggests that a long time ago, a larger, simple cell tried to eat a smaller bacterium. But instead of digesting it, the larger cell formed a partnership with it. The smaller bacterium was one of the new types that had figured out how to use oxygen for energy. So, the small bacterium lived inside the larger cell. The larger cell provided protection and brought it food. In return, the smaller bacterium shared the enormous amount of energy it was producing using oxygen. Over millions of years, this internal partner became what we now know as the mitochondrion. Every cell in your body, except for red blood cells, contains these descendants of ancient oxygen-breathing bacteria. We carry the legacy of this ancient revolution inside of us. That high-energy, oxygen-based lifestyle is what ultimately allowed for the evolution of large multicellular creatures like us. Without the Great Oxidation Event, there would be no animals, no dinosaurs, no people. We could never have evolved. Another profound change happened high up in the atmosphere. As oxygen gas O2 drifted into the upper layers, it was bombarded by ultraviolet radiation from the sun. This radiation split the O2 molecules apart. The single oxygen atoms then quickly combined with other O2 molecules to form O3. O3 is ozone. Over time, this process created the ozone layer. This layer acts as a planetary shield, absorbing most of the sun's deadly UV radiation before it can reach the surface. Before the ozone layer, the land was blasted with so much radiation that complex life would have found it very difficult to survive there. The ozone layer made the continents safe. It paved the way for life to eventually leave the protection of the oceans and colonize the land. So how do we know all of this happened? We can't go back in a time machine. The evidence is written in the rock. The banded iron formations are the most dramatic piece of evidence. Their existence and then their sudden disappearance from the rock record around the time of the Goe tells a clear story of the ocean's rusting. The geologists also look at other clues. They study ancient soil profiles called paleosols. Before the GOE, the soils are a dull gray, with minerals that are unstable in the presence of oxygen. After the GOE, you start to see red beds, ancient soils and river sediments that are reddish in color, because the iron in them has been rusted by atmospheric oxygen. They can also look at specific minerals. A mineral like pyrite or fool's gold can be washed down a river and settle as a rounded pebble in an oxygen-free world. But in a world with oxygen, pyrite quickly breaks down and rots away. So when geologists find ancient riverbeds full of rounded pyrite pebbles, they know the atmosphere at that time must have been anoxic. When those pebbles disappear from the record, it tells them oxygen had arrived. They also study the isotopes of elements like sulfur, which behave differently in an oxygen-rich versus an oxygen-poor environment. All of these different lines of evidence from different fields of geology and chemistry point to the same story around 2.4 billion years ago. The fundamental chemistry of our planet's surface changed for good. The story doesn't quite end there, though. The Great Oxidation Event was just phase one. After the initial rise, oxygen levels didn't shoot straight up to modern levels. They stayed relatively low, maybe just a few percent of the atmosphere, for another 1.5 billion years. Scientists sometimes call this period the boring billion, because from a geological and evolutionary standpoint, not a lot seemed to happen. Life stayed mostly simple and microscopic. Then, around 800 million years ago, something kicked the system again. We're not entirely sure what, but oxygen levels began to rise a second time, climbing much closer to the levels we see today. This is sometimes called the Neoproterozoic oxidation event. This second big breath of oxygen may have been the final ingredient needed to fuel the evolution of the first animals and the incredible explosion of diversity we see in the Cambrian explosion a few 100 million years later. The rise of land plants, much later, would pump even more oxygen into the air, leading to the atmosphere we know today. It's a humbling story when you think about it. The world we inhabit, the very air we breathe, is a legacy of ancient microbes. It was created by a global pollution event that caused a mass extinction and a planetary ice age. The heroes of the story, the cyanobacteria, were just trying to make a living. They weren't trying to build a new world. They were just releasing their trash. But one microbe's trash is another microbe's, and eventually an animal's treasure. The Great Oxidation Event shows us that life isn't just a passenger on this planet, passively adapting to whatever conditions it's given. Life is a powerful geological force in its own right. Tiny, single-celled organisms completely remade the surface of the Earth, from the color of the oceans and the rocks to the composition of the air itself. So, the next time you take a deep breath, just for a second, think about where that oxygen came from. It's not just air, it's the ghost of a lost world. It's the byproduct of a biological revolution that took place billions of years ago. It's the result of a global catastrophe that, by sheer chance, created a world where creatures like us could one day evolve, stand up, look at the blue sky, and breathe.